Hello guys, welcome to very first video of this channel. Here we will explore fascinating content in science, technology and sustainability. Let's dive in and kickstart this exciting journey together. Before I start my today's topic, I want to highlight general framework or proposed content for this channel. According to my plan, we will have two types of content. The first types of content is interactive panel discussion types of content in which expertise and professionals are invited to discuss on a specific topic in science and technology. In this discussion session, we will give priority for question or suggested topic from audience. So I would like to invite all of you to ask any question or suggest a specific topic you need to hear from panelists. The second types of content is lecture type in which me and my fellow friends select one specific topic in science and technology and present it here in detail and very simple ways that anybody interested in science behind green technology can understand. So this lecture section open eyes for audience to read or inspire the audience to read more. And also you have an opportunity to ask question for further detail on presented topic. I've been saying that today I'm going to discuss step-by-step proof of Betz Law. Before deep dive to step-by-step proof, I want to give you quick backgrounds about wind energy. Wind energy is a kinetic energy of moving air on Earth's surface. And this moving air occurs due to three main factors. The first factor is uneven heating of Earth's atmosphere by solar radiation. And that is why sometimes we can call wind energy is indirect source of solar energy. The second factor is topographical variation of the Earth. And the third factor is rotation of the Earth on its own axis and around the Sun. After human being observe this free kinetic energy in air, introduce a technique of harnessing this free energy, which is windmill, then upgraded to a current wind turbine. Wind turbine was designed to convert kinetic energy of wind to mechanical energy, then upgraded to electrical energy depending on end users. As you can see from this simple schematic diagram, here we have kinetic energy that in wind, and we have turbine tools or device that use to capture this kinetic energy and convert to mechanical energy. Then we have electric motor synchronized with wind turbine to convert mechanical energy to electrical energy. So here my today's main concept, Betz Law. Betz Law was established by German physician in 1920, and the law states that the maximum efficiency of wind turbine converting kinetic energy to mechanical energy is 59.3%, regardless of wind design or blade design and blade types. This law plays a significant role in development of or in evolution of wind technologies, and it helps to optimize the efficiency of wind turbine and also improve aerodynamic property of wind blades. This law was established and on two main assumptions. The first assumption is there is no friction while converting kinetic energy to mechanical energy. And the second assumption is assuming that wind blade is disk or solid. There is no space. That means solid wind turbine. That means all moving air hits the turbine or spins the turbine and convert to mechanical energy. In reality, when converting kinetic energy to mechanical energy, there is loss. That means there is frictions. And again, wind blade is not solid or disk. There are certain air molecules that pass over the turbine before hitting the turbine. But this law helps as a baseline in improving wind blade efficiency and also improving aerodynamic property of wind blades. So within next few slide, I will show you in detail by step approach how 59.3% obtained by Albert, or we prove this Betz law. Here, step one, draw moving airstream through wind blades or wind blade as barriers. So here we have three sections. The first section is entry of the tube or upstream of air, and we have wind blade or wind turbine. And the third section is up downstream or exit of the tube. And we have corresponding for upstream, we have corresponding ambient pressure, and also we have corresponding ambient pressure for downstream. And also we have volumetric flow of air, that means area of upstream and the velocity of upstream. And we have P1 and P2. P1 is pressure before disk or before turbine, and the P2 is pressure after turbine. Then pressure 1 always greater than pressure 2 because certain pressure captured by turbine and convert to mechanical energy. As a result, pressure 2 drop. So pressure 1 always greater than pressure 2. And we have corresponding area or swept area of the turbine and the velocity of turbine. And as well, we have area of downstream and the velocity of downstream. Then the second step is applying continuity equation, which states that volumetric flow of air molecule is constant. That means area of upstream times velocity of upstream is equals to area of turbine, velocity of turbine is equals to area of downstream, velocity of downstream. Let's say this is equation one. Third step is calculating force on turbine due to change in momentum. So force on turbine obtained by mass flow rate times change in velocity. So from mass flow rate can be calculated from volumetric flow rate times density, which is density times area of turbine, velocity of turbine, or area of upstream, velocity of upstream, as continuity equation work here. Then change in velocity is equals to velocity of upstream minus velocity of downstream. Then substitute these two equations in place of mass flow rate and the change in velocity. We obtain equation 2, for force of turbine. Keep this as equation 2. Then next step is express force of turbine in terms of pressure. As we know, pressure is equals to force over area. So pressure on change in pressure of turbine is equals to P1 minus P2 is equals to force of turbine over area of turbine. From equation 2, we know that substitute equation 2 here in terms of force of turbine. Then density, area of turbine, velocity of turbine times, open parentheses, velocity of upstream minus velocity of downstream, close parentheses. Then divide by area. Area cancelled by area. Then we have equation 3, which is P1 minus P2 is equals to density times UT or velocity of turbine times open parentheses UU minus UD close parentheses equation 3. Let's say this is equation 3. Then step 4, applying Bernoulli's equation for both upstream and downstream. So use this equation here, equation for upstream. We have pressure of atmosphere or ambient pressure, which is pressure at infinity, plus 1 over 2 times kinetic energy of this moving air of upstream, which is equals to, we have pressure 1 here, plus 1 over 2 kinetic energy in moving turbine. Let's say this is equation for upstream. The same equation again applies the same principles, I mean Bernoulli's principles for upstream. Here uh, we have P2 plus kinetic energy in moving turbine. That means density times UT square, which is equals to, we have here ambient pressure plus 1 over 2 times density times UD square for downstream. Then sum up these two equations. Then we have ambient pressure at upstream. Again, we have ambient pressure at downstream. So these are similar or equal value, identical value, but opposite directions. So it cancel each other. Again, here for turbine, we have the same identical value for upstream and downstream. This also cancel each other. We have new equation, which is equation 4, P1 minus P2 is equals to 1 over 2 density U density times open parenthesis UU square minus UD square, close parenthesis. Let's say this is equation 4. Then substitute equation 3 in equation 4. That means we have P1 minus P2 here. Again, we have P1 minus P2 here. So substitute this equation 3 in equation 4 and then solve for velocity of turbine. Here, this equation 4, that means UU square minus UD square can be expanded or factor out as these equations, as you can see. So that means UU open parenthesis UU minus UD close parenthesis times open parenthesis UU plus UD close parenthesis, then divided all the way by UU minus UD times density, then solve for UT. Then velocity of turbine can be calculated as 1 over 2 open parenthesis UU plus UD. Let's say this is equation 5. The next step, or step 5, calculating efficiency of turbine. We know efficiency always is equals to power out over power in. Power in can be calculated from it is a flow rate or rate of kinetic energy. That means power in is equals to volumetric flow rate of upstream times velocity, that means velocity square or kinetic energy. So this can be rewrite as power in can be calculated as 1 over 2 density times UU times U cubed. Let's say this is equation 6, or power in of inflow winds. For power out, that means power of turbine can be calculated as force of turbine times velocity of turbine. From bring up equation 2 in place of force of turbine, then this equation became density area of turbine, velocity of turbine, UU of turbine times open parenthesis UU minus UD times UT. So UT times UT became U square. Here we have this equation. Power out is equals to density area of turbine UT square times UU minus UD. But from equation 5 for UT, we know that 1 over 2 UU plus UD, or velocity of turbine. substitute this equation in here, then that means in place of this, 1 over 2 square is 1 over 4, then density area of turbine times this square can be rewrite as this polynomial. That means UU square plus 2UU times UD plus UD square close parenthesis times UU minus UD close parenthesis. So simplify this equation and factor out UU. Here we have this simplified equation. That means this all simplified as density area of turbine UU square times factor out UU square for this. That means divide all for UU square. Here we again for this bracket again for or this parenthesis again factor out UU, then divide UU for both. Then we have equation 7, which is density 1 over 4 density times area of turbine UU cubed times 1 minus UD square over UU square close parenthesis times one, open parenthesis 1 plus UD over UU close parenthesis. Let's say this is equation 7. Then substitute in efficiency equation here. Equation 6 for power in, equation 7 for power out. Then this is equation 7, this is equation 6. Then cancel out this similar value. That means this is continuity equation. That means UT times UU cubed is similar with AU times UU. So this cancelled by this. And 1 over 4 cancelled by 1. That means divided by 1 over 2, it's became 1 over 2. Here, equation of efficiency can be rewrite as this. Then for more simplification, let's assume UD over UU is equals to X. Then substitute X in this equation. Then equation of efficiency became 1 over 2, open bracket 1, minus X squared, close parenthesis, times, open parenthesis, 1 plus X, close parenthesis, multiply this all and differentiate as a function of X, first order derivative, and say it is equals to 1. That means to calculate critical value minimum or either minimum or maximum value, first derivative of polynomial should be equals to 0. So this became quadratic equations. So using quadratic formula solve for X, and we found that X is equals to minus 1 and X is equals to 1 over 3. Then whenever you substitute minus 1 in this equation, C is equals, efficiency is equals to 0, which not makes sense. That means turbine is not working. So we don't use minus 1 as value. Then substitute 1 over 3, C is equals to 32 over 54 or 16 over 27, which is equals to 0.593. This is all about Betz Law. I believe you grab something new or add something new concept on what you have before. That's all for today. Thank you for watching. See you next time with new concept. Don't forget to subscribe, comment, ask question. I will address in the next video. Bye bye.